remember how the derivative of the Lagrange function is going to be defined. Phi of x was the sum from 0 to infinity of the fk of x. So what's an expression for the derivative of the Lagrange function? It's this expression here, right? True enough? True that. So all I've done is form the Newton quotient for the Lagrange function out here and express it in terms of this little increment delta f. And then I would have a corresponding sum on the other side, where the k's run from 0 to 1. Okay, but what, since if once k is past m, these are all zeros, can I replace this with a finite sum? For the moment, k equals 0 to 2m, right? And let's call it epsilon k. Epsilon k is plus or minus 1, right? It's the Newton quotient evaluated for various k with a particular delta m. Whenever k is less than or equal to m, it's plus or minus 1 whenever k is greater than m at 0. So this thing gets trimmed out to a finite sum. All right. Now, if I take the limit as delta m goes to 0 over here, what do I get? If the limit exists, right? If the limit exists, I get that. What do I get over here? I can either add or subtract 1 as m gets bigger and bigger, right? It's a string of pluses and minuses all spread out. Is this ever going to converge to a limit? As delta m goes to 0, m gets larger and larger. More and more of these things are added together. But what are you adding each time? You're either adding or subtracting a 1. Can that ever converge? There's no limit. End of story. And that's for any point x. Does not exist. Do not enter.
Do not result.
That's for T and R. Yeah. I think this is the simplest explanation I can come across. People rediscover this every once in a while. I think that's what happened. No one's basically somehow got that into the American Mathematical Monthly or something back in the 80s. This seems to make more intuitive sense to me. You've got a finite sum, pluses, plus 1s and minus 1s. And then you let the top index of that sum run off to infinity as the delta m's get smaller and smaller. On the one side, it's the definition of the Newton quotient for the derivative. And on the other side, it's this jerky sum that just, yeah, you could add a bunch of 1s, well, that's not good either. You go off to infinity. So if you had equal numbers of 1s and minus 1s, the thing could just oscillate. It just never settles down. Right? What's the condition on the the terms in a series, what is the absolute minimal condition for the thing to converge? The sum of ANs converging. What has to happen? The limit of the ANs as n goes to infinity has to be 0. Of course, that never happens here because you've got plus and minus. So anyway, that's it. What a strange thing. Continuous nowhere differential function. There's an argument, maybe we can go into, where you show it indirectly by counting functions. You know, the number of functions on the reals is what? Well, the reals have, if you believe in the continuum hypothesis, the reals have cardinality Aleph 1. And then you raise that to the Aleph 1 power, right? Which is sort of greater than Aleph 1. So there are intrinsically more functions from the reals to the reals than there are real numbers. That's pretty believable. If we show that somehow the continuous functions have a certain cardinality and the differentiable functions have a lesser cardinality, what can we conclude? That there's a whole lot of continuous but not differentiable functions out there. You know, if there are lots and lots of continuous functions, that's a higher order of infinity than the number of differentiable functions. What do you say? There have got to be continuous nowhere differentiable functions, right? So let me see if I can address that sometime next week. It's just kind of another way to see this. You don't get a function. The beauty of this example is an example. You can see how you really see how it works. The little soft teeth are just so numerous and going every which way. When you add them all up, it just blows up any chance of you having a derivative. The derivative is just bouncing around so much, you don't have it. It's a constructive proof. A non-constructive proof is somewhat less satisfying. It's like the irrationals are uncountable. How do you prove that? Well, you show that the real numbers are uncountable, the rationals are countable. Take the difference. It must be that the irrationals are uncountable. Greater. You ever prove that directly? No, that's pretty much it. What we do. And a proof based on the idea of category, mere category, is the way you get at this notion of continuous but nowhere differentiable in the large. Most functions that are continuous are differentiable. Isn't that a kick in the head? It's like most real numbers are irrational. In algebra, we remember Dave went through that. It wasn't until the 1840s that anybody actually exhibited a single known transcendental number. And most of the real numbers are transcendental. The algebraic numbers are countable. The whole shebang is uncountable, so what makes up the difference? The non-algebraic numbers. But they were hiding. It's like the tip of the iceberg. We never saw it. It's been there all along. And in fact represents most of the numbers. We just didn't know. Silliness. Anyway, there you go. So that concludes chapter 2 with the bank.